Okay, so we start this new session about the game changers in Earth observation. So hello everyone, I am Annika Znap from the International Space Science Institute in Bern. And it is my great pleasure to welcome Yann Kerr today for this, I think it is the fourth lecture in Earth Science since we start this new series. So I will briefly present Yann. Yann Kerr is a senior scientist at CNES, that is the French Space Center in Toulouse, and he is also the director of CESBio, also located in Toulouse, a research lab that conducts research on the continental biosphere and on its interaction with climate change and variability and its interaction with human activities. So CESBio heavily relies on satellite data, but not only, also in situ data and modeling. Yann research fields include the theory and techniques of microwave and thermal infrared remote sensing of the Earth, with application in hydrology, water resources management, and vegetation monitoring. He has been involved in many space missions from the conception to the launch, and also he has been and still involved in post-launch validation, as well as to the scientific exploitation of the data. Yann has been principal investigator or co-investigator of several missions from the European Space Agency, ESA, and also from NASA and from CNES, the French Space Center. In 1990, he developed interferometric concept applied to passive microwave observation of the Earth's surface. And in 1997, he proposed the development of the SMOS mission, which is the topic of his lecture today. SMOS means soil moisture and ocean salinity. It is one of the missions of the Earth Explorer program of ESA, and it was launched in 2009. So it is dedicated to measure soil moisture and sea surface salinity, that is to study the global water cycle. Yann is a lead investigator of the SMOS mission and the chair of the Science Advisory Group. He also coordinates SMOS science activities in France. And in that context, he has organized several scientific international workshops to discuss the SMOS science. He's also a member of the science team of the NASA Smap mission. Smap means soil moisture active passive. It is also dedicated to measure soil moisture, and it was launched in 2015. And finally, I would like to add that Yann has published a very large number of articles, more than 400. And over the last 3 years, successively for the last 3 years, he has been declared highly cited researcher from the Web of Science. And several of his papers received more than 1,000 citations. So now I stop here, and Yann, the floor is yours for about 45 minutes.
Thank you very much, Annie, for this introduction. I will now try to share my screen, hopefully. And we'll start my presentation just now. So I would like to
we lost you, Yann. We don't hear you.
Sorry, I pressed the wrong button.
Okay.
So
start again.
I thank Annie for the introduction and EC for giving me the possibility to make this presentation and this talk about SMOS. And I will try to give you a quick overview of SMOS within the 45 minutes I am given. So This talk has been made with contributions from many people, and in particular from other members of the SMOS team at CESBio, but also Roberto Sabia and Jacqueline Boutin for many of the slides, plus the ESLs, of course, and I would like to thank them. But first of all, after this mission and so many years spent working on this, I would like to give first thanks to many people who made this possible. So first of all, and not the least, special thanks to Philippe Althofer. He was with me to write the very first proposal, and it was a huge effort. And all along the years of SMOS, he was a very strong help. But of course, also, I would like to thank two of my colleagues. We were at the start of this big odyssey. In the late 80s, Jean-Marc Goutoul and André Lannes, and some other partners like Eni Njoku and Tom Schmugi, with whom we discussed a lot, and everything that stemmed this SMOS big campaign, I would say. I would like also to thank all the colleagues at CESBio and in France, many institutes in France and in other countries. I tried to put a list there, but obviously I've forgotten many. Sorry for them. I tried to be exhaustive, but it's impossible. But I would like to thank all those who were participants in this big event. But also the teams at ESTEC and CNES who developed the instrument and the platform, the mission managers, the people at the operations without whom we wouldn't get any data, and they're doing a magnificent work to provide us with the data very quickly, and of course all the related industries also contributing. I would like also to thank some of the managers who at the very beginning had the vision and I would say the guts to support this crazy idea and enabling us to have this mission flying in space just now. And I must say, my experience recent is that it's a very endangered species. The presentation will go through a brief background to have everybody up to speed on what this mission actually does, the rationale for the SMOS mission, and some of the results, a very skimming on the top surface of the results. And I'll finish with a couple of slides on the potential new steps. But the first challenge, of course, is to compact in 45 minutes all this, the mission, the results over oceans, over land, over the cryosphere, the operation uses. And the other very astonishing results we got on very unexpected fields, and I will show a couple of them. But let's get started. So the idea is to look at the surface, and if we think of the surface of a land, we have vegetation on top of it. We have a number of things, clouds, rain, and all the rest of it. And if you look at the spectrum going from the visible to the microwaves, we know that we are looking at different wavelengths. So we have different penetration depth. The optical, as we know, is blocked by the clouds. Vegetation obscures the surface, and the penetration depth over bare soil is a fraction of a micron. We can go up to higher frequencies, to thermal emission, and then to microwave. And microwaves have the big advantage, the longer the wavelength, to penetrate, go through the vegetation, go in not too shallow depth in the ground, so we can see with some inertia the surface and have a better grasp on what's actually going on near the surface, and so on and so forth. So the idea of SMOS is to look at the microwave part of the spectrum and to be efficient to go at the lowest possible frequency. I won't talk much about radars. We took the option to use passive microwaves because radar is a coherent signal and it's, as you know, an emitted and reflected signal. So the signal itself is very much affected by structural parameters, which is not so much the case with passive microwaves. So we have a signal which is more significantly related to the characteristics of the surface, either sea or land or vegetation, than with other active systems. And that's why we prefer to use radiometry. But of course, we have to select the frequency. So passive microwaves is a large spectrum. And if you look at the sensitivity of the signal as a function of frequency on the plots here, for both ocean surface here and on the top land surfaces, you see that when you go to lower frequency, typically 1 gigahertz, you have a higher sensitivity to salinity over land with low sensitivity to wind speed or surface temperature. And for the land, it's the same, high sensitivity to surface soil moisture, less to vegetation biomass, and so on and so forth. So we want to go to low frequencies. But also we are limited to other factors which cannot give us complete freedom. First of all, we've got to be able to look at the surface, not at man-made emissions. So we have to put ourselves in protected band, and we're using the hydrogen line where we have no emissions. It's a rule accepted by everybody not to emit in this band, which was reserved for radio astronomers at the beginning, but proves very useful for us. And as you see, the wavelength is 21 centimeter, which means vegetation elements, for instance, are most generally of a smaller size than the wavelength. So hence the possibility to go through it. The challenge, however, is that we need a very large antenna. The antenna size is linked to the frequency. And the general rule is that the aperture is proportional to the wavelength divided by the diameter of the aerial. So if you're flying, say, at 700 kilometers above the surface as a classical satellite, you need an 8-meter antenna to get a 50-kilometer spatial resolution, more or less. So this is the main constraint we have to cope with. And for this, several options were considered. The first one was SMOS. So we used the concept of interferometry. I will detail it afterwards. But you can also consider a large antenna with a push broom approach. This was selected by the NASA mission Aquarius, which flew in 2011 to 2015, or a conical scanning antenna. And this is Smap, which was launched in 2015, and which has a 6-meter antenna, giving us a resolution of about 45 kilometers. Of course, the next parameter to consider is the sensitivity of the signal to the surface. And the larger the antenna and the more field it is, the better the sensitivity. So in our typical case, the Aquarius mission was designed for having a maximum sensitivity because it was aimed to look at the oceans. The Smap has also a good sensitivity, while the radiometer, like interferometry radiometer like SMOS, has a reduced sensitivity. You see 3.5 Kelvin, but I will tell you how we go through this afterwards to avoid this little drawback. A couple of words on interferometry. We are looking at the scene with the several antennas, and we're looking at the correlation products between different antennas. And to make things very simple, we can say that roughly this system makes a Fourier transform of the scene, and it enables us to have a resolution which is equivalent to an antenna having the largest dimension separation between the maximum antennas. This is the basic principle. It is not new. It has been used by radio astronomers. This is a Socorro system. It spans over miles, and it's made of antennas which are bigger than SMOS itself. But it is the very basic principle we used when we thought about making SMOS. This has a big advantage of enabling a large antenna easily deployable, but the drawback of having a reduced sensitivity, as I said. The principle has one advantage, which we try to make full use of, is that the system images a whole area of the Earth for each integration times. So as the satellite moves along its orbit, a given point on the surface is seen with a number of angles. And by accumulating all these acquisitions, we can get something equivalent to long integration time, and thus improve significantly the radiometric sensitivity, which is crucial, as I will explain in a couple of minutes. So the advantage of this system is that it is multi-angular. We have a large swath. We have a fully polarized system. And a very significant advantage is that we reconstruct the points. So we are making exactly the footprint we want within the limitation of the system, of course. So for each overpass, we can aim at the same point. And for each equivalent integration time, we can have the same point be seen. We don't have any smearing effects as with conical scan or push broom systems. But the challenge, next challenge we have to cope with is that for retrieving sea surface salinity, we need a very high sensitivity. On this curve made by Gary some years ago, you see that we need a sensitivity of a fraction of a Kelvin if we want to be able to reach the 0.1, 0.2 PSU we would like to attain. PSU being the unit used for salinity measurements, which is a percent salinity unit. And you see on this little plot on the left-hand side, right-hand side, that over the open ocean, the range of variations we can expect from such a system, L-band radiometer, for the range, usual range of salinity is of a few kelvins, typically 4 to 5 kelvins. And this is from what we got to extract the salinity signal. So as seen like this, it seems fairly impossible. But it is possible, and we'll see it. Just a couple of pictures to show you what the satellite looks like. This is the satellite when it was in the testing center at ESTEC and the solar simulator. You see the little man in blue here. He's got a mask, not because of COVID, but because he's in a clean room. But you see the sheer size of the antenna. Typically, the diameter is 8 meters of this system. And this is when it was in Cannes, in Thales, for the integration, where you see the bus made by Thales for the Proteus bus, and the instrument on top of it. And you see that the instrument is bigger than the bus and bigger than the people looking at it. So it's a big instrument, actually. The third challenge we had to cope with, and this was not really foreseen, because it was discovered after launch and in spite of a number of previous studies made before that, that even though we were operating in a protected band with ample margins to avoid out-of-band emissions, the data was riddled with radio frequency interferences. A number of actions were taken. There is now a RFI group working continuously at ISAC in Spain, monitoring the sources. We are also monitoring them, and we are reporting any source and doing requests at the ITU to get them suppressed. So in some cases, we saw a decrease of the number of sources, but it is still present in many areas. And the subsequent missions could capitalize on the results and implement a slightly more sophisticated method for Aquarius and a very sophisticated method for Smap to filter some of the RFIs. So typically, this is how it goes. We've got the passive band, which is protected. And for SMOS, we took a good part of margins. Instead of using the 27 megahertz available, we used only 19, which is a small amount. And as you might know, this impacts directly the sensitivity. So we reduce the sensitivity by reducing the beam width. But nevertheless, this is a bad image, but it is typically what we can have. So you see the regions where there are unrest or wars or activities like this, it's riddled with illegal military RFI sources, very often emitting in the band. And recently, last July, we had in China a huge source starting, and you see it's completely obliterates the signal. It is reduced now, but it's still present. And Japan also has a broadcasting system which emits locally, giving no data over Japan. So these are our main issues. Some areas are totally free from RFI, Australia, New Zealand, obviously Antarctica, and a good part of the Americas. So this was our third challenge. So to sum up, the unicity of passive L-band measurements, we are operating at low frequencies, so we have reduced sensitivity to atmosphere and sun irradiance, much reduced sensitivity to the structure of the observed targets. We are making measurements not only at low frequency, but also in the passive domain. So we have a good penetration depth. We are sensitive to sea surface salinity. We are able to measure thin sea ice. And we have a very high sensitivity to soil moisture within the first centimeters. We are making direct measurements of soil moisture and sea surface salinity, no proxies, no scaling. So the data is usable in applications. And this was visible from SMOS because a few months after the launch and the delivery of data, operational applications started to emerge, whereas with other sensors, after sometimes decades of measurements, there were still no application measurements in those fields. So the way we got access to sea surface salinity and soil moisture proved to be very unique. The cons of this, of course, is the spatial resolution and the RFI, as I just mentioned. So then, to put everything in a nutshell, this is a summary of the measurements, so 2D interferometer, etc. We have a revisit of less than 3 days, and we are measuring data both at ascending and descending paths, which is typically 6 a.m. and 6 p.m. The system is still in good condition, even though it's more than 11 years old. And we are regularly going through mission extension reviews to get it going further and further in time, as long as everything is working properly. The measurements we were making with the SMOS were entirely new. There was a quick or small campaign with the Skylab in the 70s, but that was all. So we had to work on the algorithm with no data to use as for any mission for making measurements for the first time. And this led to a lot of things to be sorted out before launch. And we were quite happy to see that even though we were starting from scratch, soon after launch, all the algorithms were running smoothly and delivering data, even though they were not as good as what we expected. And we are working on improvements on these retrieval algorithms. And what we are obtaining now cannot be compared to what we had 9, 10 years ago. There are huge and drastic improvement in the results. And we have operational users. This is where you can access the data. All the data is available to anybody, of course. So, summarize, was it a game changer? It's the first operational L-band radiometer. It is the first interferometer in space. It is the first direct and absolute measurements of soil moisture, the first ever measurements of sea surface salinity, as well as the first measurements of thin sea ice, liquid water in snow, vegetation water content, rainfall estimates over land and oceans, hurricane monitor, etc., etc., etc. And this is only to name but a few. Now, is it an old story already? You see here the proposal we submitted to ESA some time ago. And after 11 years, we have all the components are nominal. We have still plenty of fuel and power. We have the degradation of one of the protection on one of the arms. It's warming up more than it should, but currently there is no impact on the data. And the last measurements done by the ESA team shows that it's stabilizing now, or it seems to be stabilizing. In itself, the measurements are very stable in time. These measurements are the SMOS and Smap measurements done over Dome C in Antarctica, where we thought that we would have a perfectly stable target. Actually, as you see, it's almost stable, but not completely. There are bumps, especially here at H polarization, the bottom one. But nevertheless, you see that from the date Smap was launched in 2015, both SMOS and Smap give exactly the same measurements, which open a new research field, because as you see in H polarization, there are brutal variations of the signal, and we are not sure exactly what's happening. People are starting to investigate this, and it's not the instrument, because both instruments with very different technologies are seeing exactly the same effects. The main issue we have is the RFI, but again, the level 1 team is working on new algorithm, and they are being tested for future implementation to compensate or filter out those RFI effects. Publications, it seems to be a good moment to show the number of publications. As you see, we are in the around 160 publications per year, roughly. And since launch, it has increased steadily and seems to be going on, still increasing. So we are quite happy also with the scientific impact of this mission. So now I will go to this main contribution of SMOS is looking at the water in different phases, and we look through the dielectric constant at its evolution. So we are addressing the water storage, be it soil moisture, vegetation water content, water bodies, and things like that, but also liquid water in snow and sea ice. We're looking at fluxes. I will show a couple of examples, plumes, circulation in the ocean, and so on and so forth. And on the little animation here done by with data from FMI in Finland, they're monitoring the freeze-thaw cycle, and through this, they can see the evolution of the methane emissions from the surface, as it is directly linked to when the soil is getting thaws, the methane occurs, and they're monitoring the carbon emissions. Now we'll go through a few examples. I will start with the sea surface salinity. At the beginning, we thought we could mainly address the ocean circulation, which is already a very large topic, and it has been addressed. But very soon, the people working with the data found a number of other applications, either in marine biology or biogeochemistry, or phenomena like La Nina and El Nino and the climate indices which were derived from it. Some very significant and not very well-known upwellings in the Pacific, to the tracking of tropical cyclones in different areas. I will show you now a few examples from this. The first one is the circulation. On the right-hand side, you see something which was seen very quickly by Nicolas Reul and his team. It's the outflow of the Amazon, and you see the non-so-salted water going up the coast in bluish, and then at one stage in summer starting to go east. And this is a phenomenon also which was not very well known, but it's the outflow of and the dispersal of the fresh water coming from the Amazon. And on the left-hand side, you see a more recent series made with the SMOS data over the Gulf of Mexico. And you see the outflow of the Mississippi River and its evolution with time and the mixing within the Gulf of Mexico. So typically, this is things people had never seen before SMOS. The other outflow which was of interest and which was followed more recently is by Reverdin Company, was to look at the outflow of the Ganges-Brahmaputra River here. It's also for the Irrawaddy here, but we look at this one, And the river outflows goes along the coast of India. It's called by the Indian fishermen the river in the sea. So with low salinity. And with SMOS or Smap for that matter, we can monitor it. And you see on this off-model plot on the right-hand side, the evolution through time of the salinity along this path, along the Indian coast. And you see that it goes either very low up to Sri Lanka or middle of the Indian continent, depending on the year. And Akhil related this to the Indian Ocean Dipole, the IOD, and he saw that there was a strong correlation between these two, and actually these two phenomena are directly linked. And as you know, the dipole is between the waters on the both part of the Indian continents and the coupling with the atmosphere. Upwellings, this was found by Allory, also Gaël Allory, also right at the beginning. You see it was published less than 2 years after the first data was delivered. And it shows how an upwelling can be characterized here in the Panama area with the gap winds forcing the water and the Panama upwelling, leading to large mixing and of salt water through this upwelling, and of course implication for fisheries and the food chain in this area. This phenomenon was also not really known previously to the SMOS measurements. Related to climate indices, Audrey Hasson monitored the evolution through time of the salinity in the Pacific, of course, near the equator. And you see this off-model function of longitude here and time, the y-axis. And you see how the evolution of this front, if you want, varies depending on El Nino and La Nina event. And of course, this is used afterwards for understanding better the phenomenon driven by this El Nino event. One of the things which were quite astounding when we were looking at the data, it was also Joey Tenerelli and Nicolas Reul who found this. They realized that in spite of dense cloud cover, rain, heavy rains, during cyclones and hurricanes, SMOS could see the surface through the roughness and derive wind speed. All the other sensors saturate for such high wind speed, typically 70, 80, 90 meters per second. And SMOS and Smap now can derive the information about the wind speed below this huge cloud cover and rain and all the rest of it to a very good accuracy. And this data now is used operationally for the tropical monitoring or hurricane monitoring session. And here you see different events, tropical cyclones and high wind speed during the first 10 days of October 2018, with a number here of cyclones, hurricanes, and some other events elsewhere. Usually they are born here and they travel here. Another plume, this one in the near the Arctic. We were very impressed by this because, as I showed on the first slide, the sensitivity of the signal to salinity decreases with temperature. And around 0 degrees, it's very weak. So we didn't expect to have much measurements and hope that with the accumulation of data, we could improve the quality of the signal and get some insight. And actually, the people from l'Océan managed to get this information. And you see here, so you see here the Arctic, you see the outflow of in the Laptev Sea or the Lena River. You see in the Kara Sea, the Ob and Yenisei outflow. And you see the different incomes also here from the different areas. So we are now able to monitor even in these areas, very cold areas, what's going on in terms of salinity and thus the current and the variability of the waters in this area. So it's also a very significant outcome. And last, maybe, now the data can be assimilated, and this was done by Kerr in GMAO. And he looked at what was done when you assimilate SMOS data or other L-band data in the system with respect to when you don't assimilate it. So here you have the runs with the simply the classical data set. Here using either Aquarius or Smap, here using SMOS. And here you see when you look at the mean forecast, so this is in black what happened. And in cyan, when you're using SMOS in the assimilation, in a yellowish brown, when you use Aquarius Smap in this case, and in red, when you use nothing. So you see the drastic improvement when you use L-band data in mean forecast for that precise case for the weak El Nino event. I'm going to switch to land now. And basically what we're looking at is this basic equation of the storage, be it in the soil, in the vegetation, in snow and ice, in the rivers, or in the deep soil depth in the ground, is equivalent to what comes in, the precipitation minus the evaporation and the runoff. And here we have the different ways we can assess these different quantities from space. And I will show you how Smap can address some of these elements in the couple next slides. But first of all, when you got such a type of measurements, you want to validate them and you've got to compare it to ground measurements. And sometimes it looks like a beauty contest because people are always trying to demonstrate that their data is the best. This is simply a first slide to show in a Taylor plot diagram, so you might be familiar with it. The angle here characterizes the correlation coefficient, and the dimension is in polar coordinate. The radius is equivalent to the standard deviation. And you see here, with respect to ground measurements, the evolution between the previous version of the both L1 and L2 algorithm for soil moisture extraction is the number 1. And number 4 is the new one, which is being implemented by ISA currently. And you see that there is a significant improvement during this period of improving the algorithm. What I would like to say here is that, well, we're doing this, we're trying to do it seriously with ground data, but there are a number of caveats when using ground data. And first of all, you've got to know what you're talking about with the statistics and things like that. And if we want to do real validation, it is crucial that we do it properly. We need to have good representativity and good coverage, which is very difficult with the current set of ground measurements. We've got to avoid training your algorithm on the data you're using to validate the algorithm. And of course, you've got to do a proper usage of the statistic. You see there sometimes very strange ways to look at the statistics, but I won't go into this today. What I want to express is that very often people tell you this mission is better than the other because we get better results on our own backyard site. I think this is a very wrong approach, and I will try to explain why. I think the most important when the data sets are good is the algorithm themselves. So we should compare either product, but not really mission. And this was shown very well by our colleagues at Goddard and JPL. They took SMOS data and got them through the Smap algorithm. And you've got here on the top drawing, the soil moisture over the globe obtained for June 2017 using SMOS data in the Smap algorithm. And on the bottom, it's the Smap data going into the SMOS algorithm. And it's very difficult to see any difference between the two. So to say that Smap or SMOS is better than SMOS or Smap is a bit stupid if you're not comparing the same algorithm. And when we use the same algorithm, well, actually, there's hardly any difference. If we zoom, it's still work by Stephen Chan and Rashad Binlish. You see on top again SMOS through the Smap algorithm, and on the bottom Smap. And what you see is quite interesting because you see two features which are really linked to the instrument now. So basically the soil moisture retrieved are the same, but you see that SMOS has a higher spatial resolution than Smap, which we knew, but it's well visible here by the degree of detail. If you see, for instance, here the Senegal with respect to here or small details. And you see also that the Smap has a much better filtering algorithm than SMOS because on SMOS we see the impact here of RFI, and we see also it here a little, whereas SMAP is clean with respect to all this. It has a very much nicer look with respect to RFIs. So these instruments actually are behaving the same. What we developed also with the SMOS is a near real-time soul moisture algorithm. So you have SMOS data, soul moisture data available within 3 hours of sensing. And this, of course, is quite interesting when you want to follow in real time a flood, such as this one, which occurred in Australia in 2019, if my memory is correct. And of course, it is used now by the European Center for Medium Range Weather Forecast, ECMWF, because they are simulating SMOS in their weather prediction model. And they proved that they implemented it, and it has a significant impact on the forecast, as shown on this one, where you see the forecast for the next 12 hours, 24 hours, and so on and so forth until 3 days. And in blue is when there is an improvement using SMOS, and in red when there is a decrease using SMOS. So apart from some parts which are affected by RFI, we have, generally speaking, an improvement, and the longer the time, the better the improvement almost. So the SMOS is useful for our weather forecast applications. And of course, now we are starting to have enough data to look at climate, and we're not yet in the climate area, but we're starting to get close to it. And on this example made by Arnaud Mialon and Ali Mahmoudi, they looked at the anomalies in soul moisture of Australia for, I think here, 9 years. And you see through the anomaly, the period when there were heavy rains or floods or very wet events, when compared to periods of droughts, such as, for instance, 2018, which is a very dry year, as you might know, which had a significant impact. So we are starting to address these issues as well. Right at the beginning, SMOS was also used by USDA, the US Department of Agriculture, for the food security. And you see here the difference between what was the data they could have, or the estimates they could have before SMOS and when SMOS was launched. So of course, complete coverage, you get access everywhere to the data everywhere, and much finer resolution. I'm sorry. In Morocco, people use the data with a disaggregation scheme to monitor irrigated areas. And somebody in India, Sat Tomer, is now producing a 1 kilometer product, well, a 500 meter product, merging SMOS and Sentinel-1 data. And they're monitoring this with the various applications, mainly driven around water resources management, in that case, the Kanakata region. What we found also is that the measurements we have of the vegetation water content could be quite put to use to look at a number of features. I will show one example here. It's a deforestation area. It's worked by Emma Bousquet. And she looked at this area. So you recognize here Brazil. And in an area, you have burnt areas where there is heavy deforestation in red. And the blue area is an area which was not affected by deforestation, at least in a significant manner during the last 10 years. And you see here the evolution of soul moisture in blue. And you see that for the non-burnt area, it's decreasing regularly. So the area is drying. The leaf area index is increasing, meaning it might be what people call the greening effect due to the increase of CO2. And the VOD is slightly decreasing, meaning the forest might be in less good conditions, which could be related probably to this drying effect. But if we looked at the burnt areas, and here you see through the Moody's fire index, the number of fires indicated with the red curves, you see that the soil moisture doesn't decrease drastically, The LAI, the vegetation leaf area index, seems to be increasing a bit less than here, but similarly. But the VOD, the biomass of the trees, is decreasing regularly and drastically. So with the SMOS, we're able now to get access to this in a quite significant and quantified fashion. A word on the carbon cycle. Our colleagues from Germany and Sweden are looking at how they could assimilate the SMOS moisture with CO2, atmospheric CO2, to improve the carbon and water fluxes estimates. So they're working on this. It's something in progress, but they found that they could increase, improve the uncertainties on the flux estimates by using these different elements. If we go now to cold areas, I mentioned the work by FMI, Timo Hoitiainen, and he looked at the freeze thaw, which is indicated. So they monitor freeze thaw over this area using SMOS, and they infer from it the methane fluxes, which methane becoming active when the soil is unfrozen. And this is also something very significant, which they're working on. And our colleague Lars Kaleshke from, I don't know what's happening here. Lars Kaleshke from AVI is looking at the merging of cryosat, which you might have heard last week, and SMOS to infer the total coverage of ice on the Arctic. And SMOS is used for thin sea ice, which cannot be measured by cryosat, while vice versa, thick ice is only measured by cryosat. And with this, you can look at the ice extent, and you see here the plots, the evolution from the thinnest ice in yellow to the thickest, larger than 1 meter on the top. And you see the regular decrease of Arctic sea ice, which we know, but which is quantified now through these measurements. Colleagues from Switzerland this time, not far from Bern, in Zurich, are using SMOS to infer the snow wetness. And they're also looking at the melt detection using SMOS, and in that particular case, over Greenland. So they compared it to the XPGR, which is a very classical algorithm for retrieve the snow liquid water. And you see here that the two maps obtained by the two of them, but we found that using SMOS, we can look at what's happening below the ice. And in this case, still made by colleagues from WSL, you see the evolution through time of the liquid water. And this is during the summer of 2012. And you see how we can track the liquid water within the ice on this continent, which of course has obvious impact in the understanding and monitoring of this continent. We are in the same topic. We are monitoring. This is the team in Italy, led by Giovanni Macelloni, and he looks at the melting of the ice shelf in Antarctica this time. And you see in this little example of the peninsula, Antarctic peninsula, over 3 different subsequent winters or summers for them. You see that in 2013-14, the snow was about 20 days. The period during which there was melt was about 20 days, while in 15 to 16, it was more than 80 days. So we see clearly the evolution of the snow melt period through time in Antarctica using the SMOS measurements. So now to finish, what are the next issues? The next issues is mainly linked to the fact that there is not much future. In spite of all what was demonstrated by SMOS, but I could have said the same type of demonstration with Aquarius of the Ocean or Smap, we have 2 satellites now, Aquarius is dead, which are aging, and there is no follow-on. There is a small demonstrator to see potential techniques to be used in the future, but for measurements itself at the type of resolution we need, the future is rather blank. We made a number of studies. We looked at the user's requirement. We looked at how we could capitalize on SMOS, and this is a concept developed by ADS, which is a kind of super SMOS with a 10-kilometer resolution, which fulfills 80% of the need of the community. But apparently, nobody is much interested. There are many other options which were studied. ESA is studying one. There are a couple studied in the US as well. But we have no firm commitment to have something in the future, which is, I think, a big shame. So to finish, I think SMOS, Aquarius and Smap demonstrated that L-band radiometry is a unique way to address water in its different phases over the globe, due to its sensitivity to water and salinity, to the small influence of perturbing factors, and we can even, with the SMOS, infer separately vegetation water content, hence biomass, and soil moisture. So we have got a magnificent tool. In spite of its old age, SMOS is still in good shape, and it's working quite smoothly, similar with Smap. But we saw also the development of wealth of new applications using L-band. And with Aquarius and Smap, we have proven the uniqueness of L-band measurements and L-band radiometry, as well as the need to continue this type of measurements with at least the same characteristic of SMOS or Smap. Ideally, we would like to see the spatial resolution improve to satisfy emerging needs for both science and applications. But many operational applications, be it thin sea ice, weather forecasts, and NWPs, floods, hurricane tracking, fire risk management, and so on and so forth. There are a number of operational applications which have been developed. But currently, we have a demonstration. I think it's pretty amazing what was achieved with these 3 missions. We have 11 years of groundbreaking data. We have science galore over land, ocean, cryosphere, and so on and so forth, with over 160 publications per year. And we have operational users. And moreover, the more we look at the data, more we see room for improvement. So while viable and affordable concepts do exist, we don't see how to keep these measurements coming in at the correct native spatial resolution. And this seems a bit tricky thing to get going on. So the conclusion might be we have a game changer, but with no game change in the foreseeable future, and the loss of a number of applications. I will finish there by showing you a little extra thing. This is a sky map. So you see the universe, and what you see mainly here is the Milky Way, measured by SMOS. Through the calibration phases, we look at this deep sky, and by accumulating all these measurements, we have this sky map made at L-band, fully polarized, which shows that some of the maps used are not totally exact. So now, if you have any questions, I'm ready to answer them, and I'm afraid I've been a bit too long.
So thanks very much, Yann, for this very interesting lecture. I'm sure there is a lot of questions. So the participant can ask questions either by raising their hand, and they will be allowed to talk, or by writing their question in the chat. So let's see if we have questions. So waiting for the participant, I have one. So let me start. So my question is, can the SMOS and Smap data say something about the intensification of the water cycle?
Yes, I do believe this, and some people are starting to look at it. I know that before I got sick, Eric Wood started to have a close look at this. We have some insights. We've been looking, I didn't show the slides, but there have been a couple of groups working on the flow of water and the way it was recycled in the tropical regions. And they trying to see how they can quantify this into an acceleration of the hydrologic cycle. This is certainly something we can do, but obviously the longer time period we have to study this, the better, because we have to separate the artifacts linked to other more seasonal effects.
Okay, thank you. There is a question from Jonathan Bamber. I don't know, Yann, if you see the question or if I need to
see it. If I do what I've got to do, it should be in the chat somewhere, no?
So, okay, for this question, so I tell you. So the question is, SMOS measures the brightness temperature with which is a function of surface temperature and emissivity. Over land, both of these change in space and time. So how do you deal with this variation to get soil moisture uniquely?
Well, we are using a retrieval algorithm. So we are looking at multi-angular measurements. We get a first guess of the temperature both on the surface and at deep values using weather forecast estimates. So typically we're using ECMWF, skin temperature and deep temperature to get the equivalent temperature of the surface. This is one of the input. For the emissivity, that's exactly what we're trying to extract, because the emissivity gives us, through the dielectric constant, the soil moisture.
Okay, so do you see the next question?
No, I don't.
By Mosde Jameh. I don't know if my pronunciation is okay. He is a user of SMOS data in Iran. Do you see it, or should I? No? Okay, so he says, I would like to downscaling SMOS soil moisture data for Iran. Could you please recommend an algorithm to downscaling SMOS soil moisture with Sentinel or other satellite?
Okay, so the best option for you to improve the spatial resolution of Iran is probably to use the techniques using optical and thermal infrared, similar to those developed by Olivier Merlin. This would enable you to have the finest disaggregation scheme. Radar is better when you have plenty of clouds, but in your case, you shouldn't be too much annoyed by clouds. So this is probably the best option. The image I've shown around Marrakesh was done at 1 kilometer spatial resolution using MODIS data. But now you can use Sentinel-3 more efficiently. So my first option would be to use Sentinel-3. The second one would be to use Sentinel-1. It's more applicable in regions where it's very often cloudy. And obviously, but this is not fully operational yet, an approach using both would be optimal. I know that Smap is using Sentinel-1 to do the disaggregation, which is also quite efficient. But again, I think the optical one is more efficient for your area.
Okay, so thanks. The two next questions are about your last slide, about the sky map. So there is one from Jérôme Benveniste. He says, can you re-explain what you said about on the sky map?
I will try.
Okay.
I'm sorry. So this is a sky map which was made by using every so often, SMOS goes into inertial mode and looks at the sky above it. So the big advantage of the interferometer is that we are not annoyed by backlobes. and we can really measure the temperature from the sky. And we do the reconstruction algorithm as we would do over land or the oceans. And simply this time we are working in a range of 0 to 20K instead of in a range of 80 to 300K over ocean or land. And we do this acquisition during a part of an orbit, so it's a small bit, but we do it very often. So what François Cabot did here, he accumulated all the acquisition. We can assume that the galaxy is stable at the scale of a SMOS time life, and he accumulated everything. In some occasion, we even asked the calibration to be done in a given spatial configuration to acquire enough data over parts of the sky. So it's simply an accumulation.
Okay, so the next question is, do you plan using the sky map observed by SMOS to correct extraterrestrial radiation, eventually in operational soil moisture retrievals?
So yes, the idea is to use this map, and I think it's currently being investigated by the level 1 team, and it's not very much for surface soil moisture because we're talking about a few kelvins and they won't affect much the soil moisture retrieval. But for the sea surface salinity, it's an important contributor and they intend to use it. They've done tests already and the tests proved that it was better than the official one we used. But I think it's going to be implemented very soon.
Okay. The next question is by Zan Lee. Do you think the constellation of many cube satellites can help microwave radiometry in any way? Like forming a virtual antenna of very large size to increase the spatial resolution?
We do indeed. You have one thing to remember that if you deploy a number of small satellites, you might get large baselines, so higher spatial resolution, but you've got also to fill the equivalent antenna. So you need many of them. And if you need many of them, you also need to samples all the different baselines to do the sampling of the Fourier transform field. This means that you've got to have them everywhere and dense. And then you've got to do formation flying with a small element, flying within a few meters of each other, which is already complicated. You've got to keep them in formation, which is even more complicated. And then you've got to make sure that if there is debris or whatever to be avoided, it becomes very complex. This being said, there is a study at CNES, which is called ULID, where they are looking at, for the time being, they will send 3 nanosatellites in space to verify how they can synchronize the clocks, how they can fly in formation flying efficiently, and a number of issues like this. And if it works, the idea was to add such small satellites around a big one to do the processing and send data to the Earth to reach the 1 kilometer spatial resolution we would like to have. But this is for the future.
Okay, thank you very much. There is a question. Is it possible to have the video of this presentation? So the answer is the presentation is recorded and it will be visible on YouTube, I think, as of tomorrow. But Yann, you can answer directly to the participant.
If they want it, it's easily available. It's a big because I've put several animations in it. Most of the animations are from colleagues, and I think they don't see any problems to see them distributed. And as you said, it's going to be recorded and made available. So personally, I don't have any problems.
So send an email to Yann if you need something special.
Send me an email.
Okay, I don't see any more questions. But before closing, I have one about the map you showed at the beginning with the big perturbation over China. Can you comment a little about that? What is the cause?
The cause, our colleagues from ESAC in Spain did some research on it, and they found that it was anti-missile radar, which is probably not operating properly. That is, there are several of them in China. There are 5 of them, I think. And this one was already operating. It was already doing RFI for SMOS, but at a level which was acceptable. Well, not acceptable, but not damaging the data as much. And last July, it started to emit, and this is in terms of million kelvins now. So we put a complaint to the ITU. I wrote to Chinese colleagues who told me that they were forwarding this information, but nothing happened. This is a radar pointing towards Taiwan, funnily enough, even though it has a wide spectrum. You know, the center, the beam center is on Taiwan, which is kind of not funny. And currently, if you look at, I think it was yesterday's Le Monde, the French journal, there was a paper on that because somebody saw the blog I put, the post I put on the SMOS blog about it. And they made a paper about it because there is this risk, but there are many other risks with the RFIs. And most notably, things like the 5G and things like that might jeopardize several of the frequencies used for weather forecasting by affecting the water absorption bands and the oxygen bands. So it is a more general issue. And as to this Chinese source, it went very high. It went down after a little, it went high again, and now it's a reduced value, but it's still strong.
Jérôme Benveniste is asking, can the transmitter damage SMOS?
We don't think so. Well, it hasn't done yet. We can look at the sun. And the sun is a very strong source.
Okay.
But it blinds it completely. And in the long term, it might, yes, damage something. And the same applies for Smap, of course. They also have receivers, very sensitive receivers. And even though they've got a good filtering for this, there is nothing to be done. There is no data.
Okay, I see a last question. Could you explain why a larger antenna means lower sensitivity delta T?
Maybe I didn't express myself correctly. The larger the antenna, the better, because you've got a smaller beam, so you concentrate the energy. I was comparing an interferometric system with all these small antennas versus a field antenna. The field antenna will take all the energy and focus it on the receiver. The equivalent area of an interferometer is less. And the larger, if we take the SMOS design with a Y shape, the larger the arms, the smaller the ratio between the area covered by the elementary antenna and the equivalent large antenna. So the resolution decreases for an interferometric system when you increase the size of the arms.
Okay, so thank you very much, Yann. I think we can close this session. And thanks again for this very interesting lecture. And before saying goodbye to all of you, I would like to remind you that next week we will have another lecture, but this time on the solid Earth and on the magnetic field by Muir-Amandea. So bye-bye and see you next week.
Bye-bye, everybody, and thank you, Annie, and thank you, Issy.
Thank you.